Welcome to Learn with us. This is the 10th lecture of Basic Electronics. First, we will have a quick review of our previous lecture. In your last lecture, you understood how diode acts as a rectifier. You studied that there are three forms of rectifier. First is half-wave rectifier, second is full-wave rectifier, and third is bridge-wave rectifier. You also studied that their arrangement is different. It means the arrangement of all these rectifiers is different, but the output of full-wave rectifier and bridge-wave rectifier is same. In your last lecture, you also calculated peak inverse voltage for all these forms of rectifier. Now, what are the learning objectives of this lecture? In this lecture, you will study about the average or DC value of output voltage in a full wave and half wave rectifier. In this lecture, you will also understand effect of barrier potential on a transformer coupled half wave rectifier, on a transformer coupled full wave rectifier, and on a transformer coupled bridge wave rectifier with some examples. Now we will understand the average or DC value of output voltage for a half wave rectifier. We know that this is one sine wave and this total journey of one sine wave is same as 2 pi. It means this is pi and this is 2 pi. The output of a half wave rectifier is like this, where this point is pi and this is 2 pi. So how you are going to find average value or DC value of output voltage here? For finding this average value, first we find this area under the curve and then it is divided by 2 pi. So after finding this area under the curve and then dividing it by 2 pi, the final formula is Vp divided by pi, where this Vp is peak voltage. We know that the value of pi is 3.142, so on. So if we put this value here in this equation, we get V average is equal to 0.318 Vp, and in terms of percentage, this equation becomes V average is equal to 31.8% Vp. It shows that the average output value is approximately 31.8% of peak voltage for a half wave rectifier. It means if this is the peak voltage of a half wave rectifier, then its DC output or average output value will be here. This is VDC or V average, which is 31.8% of this peak voltage. So this is the average output value or DC output value for a half wave rectifier. Now, look at this example. If you have an output waveform like this, where this peak is 50 volts, this is 0 volts, then what is the average value of this half wave rectified voltage? We know that the formula of average value is Vp divided by pi. Here Vp is 50 volts. When it is divided by pi, we get 15.9 volts. So how you are going to draw this average value on this output waveform? Since this value is constant and it is a DC value, so it is drawn like this. It means it is a straight line. Okay, this peak was 50 volts, so this is 15.9 volts. Okay, this is Vp and this is V average or VDC. Okay, now we will understand effect of barrier potential on half wave rectifier. We know that the circuit of half wave rectifier is like this, where here is load resistor, this is source, and here we have voltage source, this is diode, and here we have output. Now if this is our input signal, where this positive half is plus Vs and this negative half is minus Vs, so this is input signal. Now what will be the output voltage here? We know that this diode will conduct during positive half cycle of the input signal. So during positive half cycle we get output like this, where this output voltage is equal to input voltage during positive half cycle of the input. It means here diode is on and it is in conducting state, but during negative half cycle we don't get any output. It means output voltage is 0 volts during negative half cycle of the input. So here on graph it is represented by this straight line. It means diode is off and it is not conducting here. So this is the case of ideal diode. It means here there is no barrier potential and there is no voltage drop. It means Vd is equal to 0. But in case of real or practical diodes, we have some barrier potential. This barrier potential is 0.7 volts for silicon diodes and it is 0.3 volts for germanium diodes. So in case of these real or practical diodes, during positive half cycle of the input, the output will become Vs minus 0.7 volts for silicon diodes and this output will be Vs minus 0.3 volts for germanium diode. It means we have some voltage drop when this diode is real or practical, and this voltage drop will affect the output voltage. Now look at this example. If this is the circuit of half-wave rectifier, where this is load resistor RL, it is of 1 kilo ohms. This is diode and this is voltage source, and if we have input signal like this, where this is plus 5 volts, it means this is positive Vs, and if this point is minus 5 volts, it means it is minus Vs. Okay, now what will be our output signal here? Here we take two assumptions. Our first assumption is that this diode is ideal. So we know that in case of ideal diode, there is no voltage drop. It means Vd is equal to 0. Now, what would be our output signal here? We know that if this is the direction of diode, it means if the positive terminal of diode is connected to the positive terminal of the battery, then the output waveform of half-wave rectifier is like this. It means diode is on during the positive half cycle and it is off during the negative half cycle. Now, what is the magnitude of this output voltage here? We know that in case of ideal diode, V0 is equal to Vs. Here, Vs is 5 volts. It means V0 is equal to 5 volts. So the magnitude here is plus 5 volts. And here there is 0 volts because diode is off. Now, our second assumption is that this diode is practical or real. It means it has some voltage drop. So what will be our output here? We know that if this diode is real, so this is the equation of output voltage, and if this diode is silicon, that the output voltage will be Vs minus 0.7. Here Vs is 5. It means here output voltage is 4.3 volts. It means during positive half cycle, the magnitude of this output voltage V0 is plus 4.3 volts for silicon diode. In case of germanium diode, output voltage will be Vs minus 0.3, that is 5 minus 0.3 is equal to 4.7 volts. It means in case of germanium diode, the magnitude of this output voltage during positive half cycle of the input signal is 4.7 volts. So this is the effect of barrier potential on half-wave rectifier. Now we will understand effect of barrier potential on half-wave rectifier with transformer coupling. This is the circuit of a transformer coupled half-wave rectifier where this is primary coil where voltage is V prime and this is secondary coil where voltage is V sec. This N tri represents number of turns in primary coil and this N sec represents number of turns in secondary coil. This is our input voltage source. This is diode and this is load resistor where we have output voltage. Now we know that the secondary voltage, that is V sec of a transformer, equals the turns ratio, that is N times the primary voltage. As I have mentioned in my previous lectures that if this n is greater than 1, then Vsec is greater than V prime. If this n is less than 1, then secondary voltage is less than primary voltage. And if this n is equal to 1, then secondary voltage is equal to primary voltage. Now, we know that the output voltage is equal to input signal in case of half-wave rectifier with no transformer coupling, like I have discussed in my previous slide. Now, in case of transformer coupled half-wave rectifier, this peak output voltage will be equal to peak secondary voltage. Okay, it means this is the equation of output voltage in a transformer coupled half-wave rectifier if diode is ideal. It means if there is no voltage drop. Now, if diode is practical or real, then there will be some voltage drop. Then this equation will become Vp out is equal to Vp sec minus Vd, which is voltage drop. This Vd is 0.7 in case of silicon diode, and if diode is germanium, then the equation will be Vp sec minus 0.3 volts. Okay, so this is the effect of barrier potential on a transformer coupled half-wave rectifier. We can also obtain this equation of peak output voltage using KVL. We know that if this is the positive terminal of our input source and this is the negative terminal, then this terminal of primary coil will be positive, this will be negative. This terminal of secondary coil will be positive, this will be negative. This terminal of diode will be positive, this will be negative, and this terminal will be positive, this will be negative. Here voltage is Vd and here we have V0, which is output voltage. So what will be our KVL equation here? We'll start from this point. Okay. So here we'll have minus Vsec plus Vd plus V0 is equal to 0. Now here we are talking about peak voltages. So this equation will become like this: minus Vp secondary plus Vd plus Vp out. It means peak output voltage is equal to 0. If we rearrange this equation, we get Vp out is equal to Vp secondary minus Vd. So this is the equation of peak output voltage if diode is practical or real. Okay, we know that in case of ideal diode, Vd is equal to 0. It means now this equation of peak output voltage will be Vp out is equal to Vp sec. Okay, in case of ideal diode. So this is how you will analyze a transformer coupled half-wave rectifier. Now look at this example. If you have a circuit like this where this is input voltage turns ratio is 0.5. Then what is the peak output voltage? We know that the formula of peak output voltage is peak secondary voltage minus diode voltage or voltage drop. Okay. First, we have to find this peak secondary voltage. We know that peak secondary voltage is equal to turns ratio times peak primary voltage. Now, what is this peak primary voltage? This voltage here is equal to peak input voltage. It means here peak primary voltage is equal to peak input voltage. We know that this input voltage is 170 volts. As you can see here, it means this peak primary voltage is equal to 170 volts. Now, put this value here, we get peak secondary voltage is equal to 0.5 because we know that this turns ratio is 0.5 and this peak primary voltage is 170 volts. So this peak secondary voltage is 85 volts. So what will be peak output voltage? If this diode is ideal, then this peak output voltage will be peak secondary voltage. It means now peak output voltage is equal to 85 volts. Okay, so the output waveform will be like this, where this magnitude is 85 volts. Okay, but if this diode is practical, it means there is some voltage drop, and if we take silicon diode, then the voltage drop is 0.7 volts. So now this Vp out will be Vp secondary minus Vd, that is 85 minus 0.7 is equal to 84.3 volts. It means here output waveform will be like this, and the magnitude here will be plus 84.3 volts. Okay, so this is your answer. Now we will understand the average or DC value of output voltage for a full wave rectifier. If this is our input signal, where this whole journey is of 2 pi, this is pi and this is 2 pi, then we know that the output waveform of a full wave rectifier is like this. This is pi and this is 2 pi. It means positive alterations that make up full wave rectified voltage is twice to that of half wave rectified voltage. So in this case, the formula of average output value or DC output value is like this, where this is peak voltage. As you can see, this formula is twice to that of the formula of half wave rectifier, and we know that the value of pi is 3.142. If we put this value here in this equation, we get V average is equal to 0.637 Vp, and in terms of percentage, this equation will become V average is equal to 63.7% Vp. It shows that the average value is approximately 63.7% of peak voltage for a full wave rectified voltage. It means if this is the output waveform where this is Vp, then this average or DC output value will be at a point which is 63.7% of this Vp. And since it is a constant or a DC value, so it is represented by this straight line. Okay, this is VDC or V average. So this is the average or DC value of output voltage for a full wave rectifier. Now we will understand effect of barrier potential on full wave rectifier with transformer coupling. We know that this circuit is representing a transformer coupled full wave rectifier where this is primary coil and here voltage is V primary. This is secondary coil, and we know that in secondary coil voltage is V secondary. But due to this center tapping, this voltage is divided into two equal halves. It means in this half this voltage will be V sec divided by 2, and in this half again this voltage will be V sec divided by 2. Now we can draw this circuit like this. I am drawing just this part of the circuit. This is D1, this is this load resistor, here we have D2. Okay, this is D1, this is D2, this is V sec divided by 2, this is V sec divided by 2, this is RL, and here we'll be having VD, that is voltage drop. Now I just connected this terminal of load resistor here because we know that this is ground and this is ground. So this circuit can be drawn like this. Now what will be peak output voltage here? We know that output voltage is across load resistor, and here we will apply KVL. Now if this terminal of input voltage is positive and this is negative, it means this terminal of this primary coil is positive, this is negative. So this terminal of secondary voltage of this half is positive, this is negative, again this is positive and this is negative. It means this terminal is positive, this is negative, this terminal of diode is positive, this is negative, this is positive, and this is negative. So we apply this KVL in this first half of this simplified circuit. So we start from this point. Now our KVL equation will be minus V sec divided by 2 plus VD plus V0 is equal to 0. Here we are talking about peak voltages. So this equation can be written as Vp secondary divided by 2 plus Vd plus Vp out is equal to 0. Now If we rearrange this equation, we get Vp out is equal to Vp secondary divided by 2 minus Vd. So this is the equation of peak output voltage for a transformer coupled full wave rectifier in case of practical or real diode. If diode is ideal, then we know that Vd is equal to 0. So in this case, this peak output voltage will be equal to peak secondary voltage divided by 2. Okay. So this is the effect of barrier potential on full wave rectifier with transformer coupling. Now look at this example. If this is a transformer coupled full wave rectifier where turns ratio is 0.5 and input voltage is 100 volts, then what is the peak output voltage across this resistor R? So we know that the formula of peak output voltage is peak secondary voltage divided by 2 minus voltage drop. First we will find this peak secondary voltage. We know that peak secondary voltage is equal to turns ratio times peak primary voltage. Now what is this peak primary voltage? This peak primary voltage is equal to peak input voltage. Here input voltage is 100 volts. So this is 100 volts. Now we put this value of peak primary voltage in this equation. So we get peak secondary voltage is equal to 0.5 multiplied by 100 and it will give us 50 volts. Okay. Now if this diode is ideal, it means Vd is equal to 0. So in this case, peak output voltage will be equal to 50 divided by 2 minus 0, which is equal to 25 volts. So what will be our output waveform in this case? It will be like this. Means during positive half cycle we get this, and during negative half cycle we get this. And what is the magnitude here? This magnitude is 25 volts. Okay. What if this is a practical or real diode, that is silicon diode? In this case Vd is equal to 0.7 volts. So now peak output voltage will be 50 divided by 2 minus 0.7, which is equal to 24.3 volts. Okay, it means in this case our output waveform will be like this, and here this magnitude is 24.3 volts. Okay, and in case of germanium diode this is 0.3, and after putting this value here we'll get 24.7 volts. So here the magnitude of this waveform will be 24.7 volts positive. Okay, so this is your answer. Now we will understand effect of barrier potential on a transformer coupled bridge wave rectifier. This is the circuit. We know that this is primary coil and this is secondary coil. If this terminal of our input source is positive, this is negative, it means this is the direction of positive voltage, and in this case D1 and D2 will be on and D3 and D4 will be off. So our circuit now becomes like this, where this is D1, this is D2, this is D3, this is D4, and here we have load resistor RL, and this is our secondary coil. So here voltage will be V secondary. Okay, now we can connect this terminal of load resistor here, because this is ground and this is ground. So this circuit can be drawn like this. Okay, here we have D1 where voltage drop will be VD1. Here voltage drop will be VD2. Here we have secondary voltage, and here I just removed these branches where diodes were off. Here we have load resistor where voltage drop is V0. Okay, if this terminal of secondary voltage is positive, this is negative, then this terminal is positive, this is negative, this is positive, negative, positive, and negative. Okay, so what will be our KVL equation here? We start from this point. So we have minus secondary voltage plus VD1 plus V0 plus VD2 is equal to 0. And here we are talking about peak voltages. So we have peak secondary voltage plus VD1 plus peak output voltage plus VD2 is equal to 0. If we rearrange this equation, we get peak output voltage is equal to peak secondary voltage minus VD1 minus VD2. So this is the equation of peak output voltage when we have practical or real diodes. Okay, it means if we have silicon diode, then this VD1 will be 0.7 and this VD2 will also be 0.7. So in that case, this peak output voltage will be peak secondary voltage minus 0.7 minus 0.7, which is equal to peak secondary voltage minus 1.4. In case of ideal diode, this is 0 and this is 0. So in case of ideal diode, peak output voltage will be equal to peak secondary voltage. Okay. Now look at this example. If this is a transformer coupled bridge wave rectifier where turns ratio is 0.5 and peak input voltage is 120 volts minus 120 volts, this is VP in. Then what is the peak output voltage here? We know that the equation of peak output voltage is peak secondary voltage minus VD1 minus VD2. This peak secondary voltage is equal to turns ratio times peak primary voltage. Now what is this peak primary voltage here? This peak primary voltage is equal to peak input voltage. Here this peak input voltage is 120 volts. It means this peak primary voltage is 120 volts. Now we put this value here. So peak secondary voltage is 0.5 multiplied by 120 volts, which will give us 60 volts. Okay. Now, what is the peak output voltage if we have ideal diodes? It means in case of ideal diodes, VD1 is 0 and VD2 is 0. It means peak output voltage will be equal to peak secondary voltage, which is equal to 60 volts. So the output waveform will be like this, where this magnitude is 60 volts. Okay. Now, in case of practical or real diodes, if we have silicon diodes, then VD1 is 0.7, VD2 is also 0.7, and in that case we have peak output voltage VP secondary minus 1.4, that is 60 minus 1.4, which is equal to 58.6 volts. Okay, so this is the peak output voltage in case of real diodes. So now the output waveform will be like this, where the magnitude of this output voltage is 58.6 volts. Okay, now this shows that D1 and D2 are on, and this shows that D3 and D4 are on. Similarly, here D1 and D2 on, and here D3 and D4 on. Okay, so this is your answer of peak output voltage. That's all for today. Now, what are the key takeaways of this lecture? In this lecture, you studied about average output or DC output values in a full wave and a half wave rectifier. In this lecture, you also understood effect of barrier potential on a transformer coupled half wave rectifier, on a transformer coupled full wave rectifier, and on a transformer coupled bridge wave rectifier.
Thank you for watching this video. If you have any questions, then write your questions in comment section of this video. Don't forget to subscribe our channel and share it with your friends and family. Thank you.